Lab 1. So this lab is going to have a bit of a longer introduction video because it's a bit of a longer lab. All right, I'm giving you quite a while to work on it. This lab will be due week 5, so you have 3 weeks to work on it, but there's definitely a reason for that, okay? I will say, though, that once you understand everything that you need to do for this lab, the answer is going to be under 50 lines of code. So it's not a lot of typing, it's just a lot of thought for each of those lines. All right, so please start early on this lab so that you don't get bitten towards the end when you realize there's a ton of work to do. All right, so let's talk about the topic of this lab. It's very similar to stuff we've been working on. It's called satisfiability. So this is a expression involving propositional variables, P, Q, and R. They could be true or false, some combination of those things. That's called a Boolean expression. It's just another word for that. And you can take these and ask if they're satisfiable. This Boolean expression is satisfiable if there's a way to assign values to its variables, P, Q, and R, give them some value, such that the result is true. So is there some way to make true out of this Boolean expression? And there is a way, right? You could set P to true. If you set P to true and Q to true, if you just set them all to true, it'll still work out, right? Because that'll make this side true, and then it doesn't matter whatever R gives you back. So if you set R to true, that right side will be false, but the whole thing will be true. All right, so that's one example, one way to make this. It's proof that this expression is satisfiable, and it is called a satisfying solution to the expression. Satisfying solution. Okay, so that's satisfiability. And what we're going to do in this lab is write a program that takes these Boolean expressions and comes up with all the different ways that it is satisfiable. All right, we're going to perform what's called satisfiability checking, and it's very, very useful for like testing if a program is correct. You end up with a bunch of constraints that end up being Boolean expressions. Analyzing programs, like your compiler is technically an example of program analysis, and it's doing things like this. It's checking if your if statements are satisfiable, because if they're not, if there's no way for your if statement to ever be true, that means it'll never execute its body, and the compiler doesn't have to compile the body. Isn't that cool? So that's the idea. That's why it's useful. It's very, very important in computer science, and we're going to make our own version of satisfiability checking. Okay, so next I want to review some stuff that I taught in my CSCI 41 class. Half of it is not super required, so you may not have seen it in yours, but I'm going to go over it and give you an example program, so don't worry. So the first one that you may not have seen is smart pointers. That's really not going to be an issue. It's going to be very similar to normal pointers. And then inheritance, which I will expect you to know. Okay, so let's first talk about smart pointers. If you go to the documentation page for the memory library, that's a brand new library in C++ version 11, 2011, and later, you have a bunch of cool functions and classes related to pointers. All right, so smart pointers are just fancy C++ classes that call new and delete for you. So they're easier than normal pointers, and so that's why we're going to use them in this lab. It saves us a lot of work. We don't have to call new, and we don't have to remember to call delete, and we just magically don't end up leaking memory. Okay, so a smart pointer, it's just a class that wraps around pointer stuff. You can still dereference these smart pointer things. You can still use the arrow on these smart pointer things. It just all works. Okay, and so there's 2 main classes that exist in the memory header. There's the unique pointer class and then the shared pointer class. So a unique pointer to a t and a shared pointer to a t. So these are just equivalent, essentially. They have deep down inside of them a t star. Shared pointer and unique pointer. They're really, you can treat them like t stars, and the only difference is like how you create them. You just never have to call delete. It's really cool. Okay, so let me show you an example program about this, and I'll give you this, of course. Smart pointers. So here is a fancy program that has to do with unique pointers and shared pointers. I'll show you both of them. So yeah, a unique pointer is creating something on the heap. If you make a unique pointer, it makes you something on the heap automatically using new. It calls it for you, and that thing is owned only by you. So there's no copy constructor on a unique pointer, and so it just your variable, that is your unique pointer. That's the only way you can get to this thing that you made on the heap. Okay? You use a function called makeUnique to create an object on the heap, and then you put like constructor parameters inside these parentheses. The example will have it make sense, I promise. And then it will automatically delete itself once this unique pointer goes out of scope. It's really cool, but nobody else gets it. Okay, so let me comment out the shared pointer stuff because that'll be next. But here is the make unique stuff. So here is me. I'm making a unique pointer to an int on the heap. So this is making an int on the heap and having it hold 42. And then once I have my p, I can pretend that's an int star. It's essentially just an int star at that point. So I can dereference my p and it'll print 42. Okay? And then I can make a unique pointer to a class C, which I make here on the heap. It will just automatically make it for me. And then I'm calling the constructor parameters, and there are none. It's just the default constructor, please. All right, so look at what happens. This is creating this int on the heap. I'm using it just as usual with the star dereference. It's all overloaded. And I'm making a p2 on the heap as well. And once we return 0, once we're done with main, the unique pointer notices that nobody else is using this. There's no need to have this around on the heap anymore, and it calls delete for you. So it deletes this memory. We don't see that, but it does it. And then it deletes this memory too, and I implemented a custom destructor to show you that it really is deleting it for you. It's beautiful. Okay, so that's make unique. We're going to use shared pointers in this lab though. So a shared pointer is the same idea. It's a pointer to a t on the heap, but you can copy it to and have it in a bunch of variables. Unique pointers, you can't do this. You're not allowed to have two copies of the same pointer. So like you can't copy p2 into another unique pointer. That's the point. It's not unique at that point. Okay? It's like use of deleted function. It's just trying to use the copy constructor, but it's not meant to be copied. Shared pointers are for copying. So shared pointer is something you can share among people. Instead of saying make unique and giving constructor parameters, you can say make shared and give constructor parameters. And once everybody who has a copy of this address is done with this, like goes out of scope or is done with whatever it's doing, then the shared pointer deletes that memory automatically all over again. Okay, so let's see here. Here's the same idea with a shared pointer, p3, make a shared pointer to an int on the heap, so this is holding 43 on the heap, dereference just as usual, and that'll print out 43. So there it is, printing out 43. I can make a shared pointer to a C object, and I can copy it around, totally fine. So that's a C object on the heap. I can set the variable that lives inside of that object just for fun to show you that it's going to work. Like set it to 44, and then go through the copy to get to that 44 and print it out. So it really is just like a pointer to a C. Like this make shared int, it's essentially making a pointer to an int. This is essentially making a pointer to a C. You can use it like that. All right. But the beauty of shared pointers rather than normal pointers is that it's calling those destructors for you. This was the unique pointer going away, and this was the C that I made as a shared pointer also going away. It was shared among P4 and P5. They're both going out of scope after main returns, and so they reclaim their own memory. It's beautiful. They call delete. So you don't really have to worry too much about smart pointers. It's just you don't need to delete them. Use them like normal pointers in this lab. So that's just to make your life easier. So that's what they're all about. Ask me if you're having any trouble with them. But hopefully this example is helpful. That's the first thing. The next thing that I want to review is inheritance. Okay, so let's use the standard example that I like to give in my class, and it's just the standard example that I think most people like to give. So you have a bunch of classes, and the whole point of inheritance is sharing stuff among multiple people. All right. So if you have some commonalities in your classes, you want to bring them up into a base class. So here's like a cat class and a dog class, and we want cats and dogs to inherit some shared functionality from an animal class because there's that is a relationship going on. A cat is an animal. A dog is also an animal, so they should have some similar things going on that we can share among them. And so animal will be called the base class, or the parent class. There's a bunch of different words for this. And then cat and dog will be subclasses, or child classes, things like that. Okay, so inheritance is all about reuse. So what are things that cats and dogs need to have in common? Like if I'm going to make a cat object and a dog object, like, I don't know, cats and dogs, they all have names, right? We can have that up in the base class. Cats and dogs, they all know how to like say stuff. They know how to meow or to woof, right? So they can talk. Maybe we can put that message so that we know that that functionality exists. We can override it later, but we know it exists if we put it in the base class, all right? And then we also usually need getters and setters, like get name, set name. We'll write these once and for all, and they'll just exist when we inherit from them in cat and dog, right? So like cat, like we want to have, when you call talk on a cat, have it meow. So we'll override the talk method for the cat, and we'll do the same for dog because dog should woof instead of meow, right? We'll override the talk method there as well. Okay, so that's what inheritance is all about. Let me show you my pre-made example of that with cats and dogs, of course. Oops. There you go. So here is an animal class where all those things are being inherited from. So animals, they have names as data. And then we can have a get name. I won't do a set name because why not? A constructor to set the name of the animal. And then we're going to have a virtual talk method so that it can be overridden. And it's going to be a pure virtual method. Hopefully these words are familiar to you, right? So this is a pure virtual method. It has no implementation in the base class. We're forced to override it in the subclasses of animal. Okay, so cat and dog are both subclasses of the animal class. So we use the colon like that. And then we'll do the things that we need to do. Cat and dogs, they need constructors, and we'll call the animal constructor to set the name because that's where name setting can happen. It's useful. We're making use of those constructors for our base class to set our member variables because name is existing inside of cats because we're taking it from animal, right? And then we're going to override our talk method in cat and dog. So cats can meow, so we're going to give a real implementation for this method. You usually want to say override just to remind yourself that you're overriding the method. And so meow for cats, woof for dogs. Okay? And so here I am, why not, making shared pointers on the heaps, on the heap to cats and dogs. And I can ask them to talk right now if I wanted. Or I could put them, like the whole point of using inheritance a lot of the time is so that you can make a vector of the base class object from the base class's perspective. So I can even though this is a cat and a dog, pointers to cats and dogs, I can put them in a vector that expects pointers to animals because cats are animals, dogs are animals. So here's C and D sitting in a vector. The cat is Lonzo, the dog is Chloe, and I can iterate through that vector and say get name, and it will do the right thing. And I'll say talk, and it'll do the right thing because they're pointers. Inheritance -o inheritance. And so here is the wonderful stuff going on. So it's like Lonzo says meow, Chloe says woof, and all this overriding is happening. All right, so that is the beauty of inheritance, sharing code, making sure something exists in multiple places, and using subclasses from the perspective of the base class so that you can put them all together somewhere and use their common functionality, like talk. Okay, so that's inheritance. Go back to your CSCI 41 notes if this is a bit fuzzy. I'd also be happy to help you in office hours, but this is something that's going to be very necessary to understand, inheritance, in our lab. Okay, we're now ready to talk about the lab. So let's go to the write-up. Write-up looks like this, and let's go to the code itself as well. I'll go over here in a different terminal to the code. Starter code, and it's 26 lab 01. So here's all the starter code that you'll get when you use the gimme command, stuff like that. So make sure to get all that, and then we're gonna make it all happen. So we're gonna do sat solving. So you are going to be given formulas like this. I think this example is legitimately one of the tests that I have. You're going to be given this formula in code. So we have to have some way of representing this Boolean expression in code form. And what better way to express Boolean expressions than trees? All right? So these are going to be trees. Let me show this to you. So every Boolean expression, there's going to be some subclasses going on. I'll get to that in just a second, but let me just go over this diagram, and hopefully it'll make a bit of sense. So here is the Boolean, here's the tree representation that we're going to make in code to represent the formula of the Boolean expression, P, or, Q, and not R. Do you see how that's kind of a tree? Like the outermost operation is the OR. So there's the OR is the root, okay? And on the left side of the OR is the left piece of the OR. That's the P, and P is a variable. So we'll use a variable class to represent that. And then the right subtree of the OR will be what you want to OR with on the right. So just look at the blue stuff right now, okay? And what is on the right but another subtree where AND is the outermost operation. We're ANDing Q and not R. You see that? So you're ANDing Q on the left, which is a variable, and then not R, which is the negation of, that will be its own little piece of the tree, not, and then that will have as its child the variable that's being notted, the variable that's being negated. Do you see how the blue makes sense for this formula? This is a formula, let's call it F. And I've run out of colors, so let's use red. Let's call this F. That's our formula F, okay? So our goal is going to eventually evaluate this formula, come up with satisfying solutions, come up with a map of things. So I'll go over that in just a second. So yeah, we're going to be SAT solving. That's the fancy quick way of saying satisfiability solving. We say SAT instead. That's the cool way of saying it. Okay, so we're going to discover all the different ways to make our formulas, which are represented as trees, satisfiable. All right, so all the stuff is going to be living in LogicH, and testlogic.cpp is where the tests lie. So let's look at LogicH, and let's walk through it. So this is just a helper for me to combine sets. You're going to need sets later. I don't think you need that one. But here is the formula class. It's the base class. So every piece of this tree, right here and also here, every piece of the tree, every subclass, or, var, not, and all those things are going to be subclasses of the formula class. Okay? It's the base class for these logical formulas. And formulas can be evaluated to true or false, so a Boolean. And you can extract the variable names from a formula, and then there should also be a destructor because we're going to be making stuff on the heap. So the goal is we're going to build up a giant formula that looks like this, call it F. It's the tree form of all this. And we're going to be able to say things like f.evaluate. We're going to have to come up, though, with a mapping of the variables to values, because there's no way right now, if I just give you this formula, to say true or false, because the answer is it depends, right? It depends on the values of the variables. So we need to come up with all the different kinds of mappings for the variables to their potential values. So for example, here is a potential mapping from variables to values. So evaluate needs a map from variables to true or false, right? Because then you could plug in, for example, true for P, false for Q, false for R, and then figure out which of these works out, okay? And so this will end up evaluating the formula, and I'm going to show you how to do that. It's going to be a recursive process, but this is meant to give back, because P is true, this whole thing will end up giving back true, right? Because it will be it's going to do like true for P, ORed with, like you're going to implement that, ORed with Q and not R, which is going to end up being false. And then the whole evaluation under this mapping is true. All right, that's the result. So let me show you how to do that and evaluate things. Okay? So let's see here. This is made up of, all these formulas are made up of subclasses of the formula class. So the AND, you can AND together two formulas, and what does it mean to have an AND? Well, you have a left-hand side, you have a left formula that you're ANDing with a right-hand side. Does that make sense? I hope so. And so that's how you build an AND. You give two things. You give a formula on the left and a formula on the right, which are pointers to formulas on the heap. They could be anything, right? That's why we're using the base class. It could be a giant or just a single variable. Doesn't matter, all right? So an AND is a formula. You can evaluate an AND. You have to implement that. I think I've implemented the extract variable names for you already, but you'll need that to get all the potential variables that you need to create a mapping for. That's why that's there. Definitely study all this code. So an OR is also a formula. To OR things, you need a left-hand side and a right-hand side, a left formula and a right formula. They can be as deep as you need them to be. They could be giant trees, right? Giant formulas. But you need to know how to evaluate an OR, right? Which involves evaluating the left and the right and like performing the OR. You can negate formulas, right? You can have a not. So not would be the root of a negated formula. And then inside of that, it needs to hold on to the thing you're negating. So that would be another formula, be as deep as you want, and I'll call that inside, all right? And you need to create a custom way of evaluating a negated formula, all right? And then finally, you have variables. A single variable name is technically a formula by itself, right? And so every variable has a string that is its name, and don't worry too much about this printing, that's just for the tests, but you're going to have to be able to set that name, evaluate a variable under a mapping of variables to true and false, and so you'll just look it up in the map at that point, and then get its variable names out, okay? And so finally, you're going to be using trees built up using these subclasses of formulas. For example, this one is an OR as its root, and then some left and right subtrees. You're going to be building up giant formulas, giving them to the satsolve function. That's what you'll be implementing. And it's going to create a bunch of different mappings of variables to bools. Because what is that but a single way of making it true? Like, this is a single answer, right? That's one way to make the formula true. There's multiple ways, aren't there? So you're going to give back all of them as a set of those mappings, all right? If you stare at the types long enough, I promise it makes sense. And the way that you're going to come up with all the different formulas, all the different mappings that make this formula true, you're going to use recursion, all right? And so you're going to use this helper function that builds things up. It takes some extra parameters because you're going to have to add to them as the recursion gets deeper and deeper. But I'm going to walk you through all of it, all right? So that's LogicH. You'll be implementing these things in logic.cpp. Boop. And then the tests are in test logic. But here's a lot of stuff that I've implemented for you. I've extracted the variable names. I've implemented the constructors for you. You're welcome. And then here's the stuff down here for you to implement. All right. So I want you to override all of these evaluation methods. Like, you need to say what it means to evaluate an AND. And an AND, remember, has a left-hand side and a right-hand side. Let's see if I can give you both of these at the same time. Split, something like that. So an AND, for example, has as member variables a left-hand side and a right-hand side, and to evaluate an AND to true or false under some mapping, you have to recursively, right, go down the left-hand side and go down the right-hand side, evaluate them. Yes? So that's the idea. That's how it's going to end up working. You're going to have to evaluate the left-hand side, the right-hand side, and figure out, like, and the results together, right? You'll do the same for OR, for NOT. To evaluate a variable to true or false, you just look it up in the map, right? That's essentially the base case. There's no recursion at that point. So the evaluation methods will also be recursive. You'll have to go down the sides of the tree, okay? And so let me show you how to implement evaluation. I can use this slide to do it, all right? So let's say you somehow magically come up with this mapping. That's what the other function's going to do to generate the mappings. But let's say you came up with this mapping and you gave that to the evaluation function, right? So your job as the implementer of all the different classes evaluation functions is this. Let me show you how it's recursive. Okay? You are going to see that, okay, the outermost thing for F is an OR. F, the outermost thing to do is an OR. And so the way that you evaluate the OR to true or false under this mapping of variables to values is, you know, you go down your left-hand side and your right-hand side. Those are those member variables. The left-hand side is this subtree. The right-hand side is this subtree. All right? And so then you're going to get to evaluating this. And that's a variable. You're going to implement the variables evaluation method. And that involves, right, it's a P. I'll look up P in my table, and it's meant to be true. All right? So your result for evaluating this variable is true. You're going to give back true as your answer. Okay? That's the result of the left-hand side. This is true. Okay? And then you're not done with the OR. You have to evaluate the right-hand side, which involves evaluating an AND. All right? So there's more recursion. So the AND needs to then go and evaluate itself, the left-hand side and the right-hand side. So it's going to go down the left, and it's going to evaluate the Q variable. Well, that's just looking it up in the mapping. Q is meant to be false, so this gives back false. And then we have to evaluate the not, because that will be the right-hand side of the AND. Yeah. So the not needs to then go and figure out what it's negating. So it needs to evaluate its inner body, its one subtree, its inside, we say. And this variable is meant to evaluate to false. So this gives back false. That gives back false. How about I just say F? This gives back F. There's not a lot of room here. And then that means the negation is going to negate false, and its result is true. You see how that's working? That's how you evaluate a not. You take the inside, get that value, and then negate it, give back true. And now the AND is ready to perform its evaluation. It has a false on the left and a true on the right. False ANDed with true. You just use your ampersand, ampersand. The whole thing, the whole result is false. You see that? So now this left-hand side is true, this right-hand side is false. You can finally do the outermost operation, which is the OR. I evaluated the left-hand side to true and the right-hand side to false. How do you OR them together? Well, in code, you just use the OR operator, right? And so the result of the entire formula under this variable to value mapping, which you were given, is just true, okay? And so that's how you know it's a satisfying solution. So that was a lot going on this slide, all right? Please ask me questions and start early. That is how you do it, though. It's going to be a recursive evaluation, all right? And so you're going to be implementing that evaluate method. The final thing that you need to do is come up with all the ways to make your formula evaluate to true. You're going to come up with all the mappings. You're going to create the satsolve function, which itself uses the satsolve helper function, okay? There's a lot going on there. I've given you a ton of comments. Please read through them. It's very helpful, all right? But the idea is you're going to come up with every possible mapping and try them all. It's going to take a while, but it's not a very efficient algorithm, but it's essentially the best that you can do anyway, so not too bad. So you're going to try every single possibility, right? So I've given you some extra hints about the evaluation method here. Please read all this too. Read the comments, my examples, all the stuff that I give you, all right? After you got the evaluation working, you're going to implement satsolve, which involves a recursive helper function, okay? So satsolve is supposed to take that formula, try every possible combination of values, which is these var to val mappings, create all of them, try them all, and figure out which ones were true. Just remember the ones that were true, all right? So your answer is every assignment of variables to values, every mapping that makes it true, all right? The easiest way to do that is with the helper function, and the idea of the helper function is that you're going to recursively try every possibility for your values to variables, okay? Or sorry, variables to values. So here's an example. Let's pretend that we have 3 variables to pick values for. They're x, y, and z. And just as to not give you the full answer, let's pretend that instead of true and false, let's pretend x, y, and z can take on 3 different values instead of 2. Like x could be a, b, or c, y could be a, b, or c, and z could be a, b, or c. And we want to generate all the different possibilities, all right? It's going to be a recursive process. And so in your implementation, you're only going to have 2 possibilities, and they're going to be true and false, all right, instead of a and b. That's the idea. So you're going to use this idea. I'm going to give you a general solution to this problem, though, all right? And so naturally, I'm going to give you the code for this, and you can translate it if you want, but I'm going to give you the code in Racket, all right? It's going to do almost what you need it to do, all right? So I'm going to have a print possibilities function that takes all these variables and gives them values a, b, or c, okay? So let me show you how to do it. Dun, dun, dun. This is going to be, oh, it's this example over here in Racket. All right, so this is the code. This is what you need to implement, essentially. Instead of a, b, and c, though, you just have true or false. I am going to print all the possibilities of mapping x, y, and z to values, all right? So the idea is we're going to have two parameters. We're going to have, at the start, the variables that we have not yet chosen values for. Like at the beginning, they've all been not having any values chosen. So x, y, and z, they start out as unchosen variables. And then we're slowly but surely going to get down through the recursion and choose particular values for those variables. And then they'll move from unchosen to chosen. All right? This will make sense with an example. All right? So our first call to print possibilities, because it's taking unchosen variables and chosen variables, is print possibilities of, well, my unchosen variables are called x, y, and z, and I haven't chosen anything yet. These are lists, by the way. A quote and then stuff between parentheses are lists in Racket. So you can think of them as like vectors in C++. So this is the list x, y, z. Those are the variables I need to choose values for still. And I haven't chosen anything yet. So that's the initial call to this recursive function. Everything is unchosen, nothing is chosen. All right. And here's the output, by the way. Racket possibilities. Here's all the options for choosing A, B, and C, setting A, B, and C into X, Y, and Z. So A, they could all be A, or the first two can be A, then it's B, and so on and so forth until like CAA, CAB, all the different possibilities. There are 3 times 3 times 3, right? So there's 3 for the first, 3 for the second, 3 for the third, so like 27 possibilities total. They could also all be C. And so you see how all of these are potential possibilities, because X, Y, and Z, they could map to any of those. All right, so those are how you're going to, that's going to be how you generate your variable to value mapping, but you're just going to use true and false instead of A, B, and C. All right, so at the start, when you call this function, it's going to be recursive. Everything is unchosen, nothing is chosen. So here's your first call to this function. I'll just call it P to save space. So everything is unchosen, nothing is chosen. And then you're slowly but surely going to take something out of unchosen variables and set it equal and put it into chosen variables. All right, so that's the recursive case. So when unchosen variables is non-empty, you're going to take a variable out, take the first one, let's say, and put it into chosen variables and recursively try every possibility. All right, so this is how you do this in Racket. I can help you I can walk you through this implementation if it's a little confusing. Don't worry, come to office hours. But here's how you do it in Racket at least. So give me the first thing out of unchosen variables. Call that var. So that's the thing that I need to make a choice for right now. At the start, it'll be x. So x is going to be popped off out of here, and I'm going to make a choice for x. All right, and then I have the rest of the variables. That's everything but the first. It's called rest. All right, and then here's the recursion. I want to recursively print the possibilities of evaluating or mapping all these variables to values. The ones that I still need to make choices for are the rest, right? Because I'm about to make a choice for x. And there's 3 different possibilities, so there's 3 different recursive calls. All right, so make choices for the rest under the assumption that this variable that I just popped off, x for example, is an A. Yeah, and then keep the rest of your choices already. You might have made some already. Add those to it. All right, or print the possibilities under the assumption that x maps to B, the variable that you just popped off maps to B, or print the possibilities for the rest of the variables under the assumption that x maps to C. So here is me recursively trying every option. Do you see how the recursion is working? So I can't give you every subtree, but for the first one, like we pop off x, we make choices for x. So x could be A or B or C. That's the chosen variables now. And then I recursively call to make choices for the rest of the variables. You see that? So make choices for y, z, having assumed x is A, make choices for y, z, assuming x is B. Same for C. And so these trees get pretty unwieldy. These recursion trees get large. And so let me just zoom in on this side. So now, when we call ourselves recursively again, we still have variables to make choices for, right? So the next one will pop off as y. We'll take y off, and so we have 3 possibilities for y now. We're going to save the original choices for x, though. That's A, right? So now, once we pop off y and we make a choice for it, we only have to make choices for z. So I'll call these 3 recursive functions, calls. All right. So x is still A, y is now also A. That's one possibility for y. X is still A, y could be B. X is still A, y could be C. Make choices for z now under all of those different possibilities. You see how eventually, once we get down to the base case, we have made every possible choice. See how the recursion is unwinding? And then, again, these are sub-recursive call trees. I can't show you all of them. And then finally, we have one last variable to make choices for. So we'll pop it off, and we'll make choices for z under the assumption that x is a and y is a. All right, so keep these. And then z could be either a, b, or c. And now print all the possibilities. Make all the choices for the empty list of variables under these assumptions. You see how once you get to emptiness, you've made choices for every variable. Once you get to empty, unchosen vars, you've made choices for everybody. That's your base case. Once you've got nothing left to choose, print out the mapping that you have created just now. You will eventually, once you get down to the base case, have tried all of them. You see that? Just by virtue of making all those 3 separate recursive calls here. You will be making 2 separate recursive calls because you have true and false. Okay? So that's how it works. There's your recursive case when you have something to choose still, and your empty base case. When you have nothing to choose, everything's already been chosen, use them now. In this case, I'm printing them out, but in your case, you're going to call evaluate. Okay? Because you've been making choices for true and false. Figure out if that particular mapping of variables to values gave you back true. Okay, you see that? And so the base case is when you have emptiness. And that's how you're going to implement this. Okay? So I talk about that a bit more up here, satsolve and satsolve helper. That's how you're trying all these possibilities for the variables. And so let's go back to that code now. So let's see here, that was logic.cpp. And so satsolve is you're just given a formula, you start it all off. Okay, here's a map of solutions that we're going to add to and eventually give them back, but we're going to call satsolve helper with the correct starting values. And the starting values are everything is unchosen. You find all the variables in your formula. For example, this has p, q, and r. You're going to get them all out with the, let me just show it to you. You'll get them all out with the extract var names method, right? And then you will put them all in your unchosen section when you call the recursive helper function. Okay, everything is unchosen, nothing is chosen. And you're going to keep on adding to this solutions map, the solution set of maps every time you find a satisfying solution. Okay, so the starting value, though, is you're going to call this with your formula everything. You're going to extract every variable from your formula, and they're all still remaining. You have to make choices for them. So you haven't made any choices yet. This will be an empty map to start out, and then the satisfying solutions is this reference parameter. Just pass this along so you can add to it and end up with a filled set by the time this has tried every possibility. Okay? So hopefully that makes enough sense. Read all these comments. Remaining vars is the variables you still need to make choices for. Choices for vars is your map so far of variables to values. Like maybe so far you've picked that p should be true and q should be false, and now it's your turn to pick values for r recursively. Something like that. So that is your choices so far. And once you have no remaining variables, you're in your base case. You made choices for everybody. Now you have a mapping to evaluate, yes? And so once you have a mapping to evaluate, once you're at your base case, there are no more remaining variables, check if f is true when you evaluate. You'll do f.evaluate under the mapping that you've just built up. Here it is. Those are your choices for variables. You see how it's all kind of coming together? Do yell at me if you're having any questions about this, but this is just, I promise it makes sense if you stare at the code and read the comments long enough. All right? Check if f is true, because then if it's true, you found a satisfying solution, and your choices for vars, see how it's a map of var to bool, and this is a set of maps of var to bool. If this one works, add it to this set of satisfying solutions. Do you see that? That's how we keep track of which ones worked and which ones were satisfying. All right? If you're in the recursive case, you have to pop somebody off. Get rid of a remaining var. One way to do that is just like get the first one. Remaining vars that begin is one way to do that. And chop off that one from the rest so that you can make recursive calls, right? So you're going to make a choice. You extract your variable, create a brand new set of remaining variables, because that'll be what you use in your recursive call, because you just are extracting this one. Like that was your, you just made a choice for p. You still have q and r left, so you got to keep them in your remaining vars set. But you got to take p out. And then you'll recursively try to solve the formula using that variable set to true. So you're going to change the map. You're going to add to it. Add that variable, maybe it was p, set it to true. and then also try it if it's false. So that way, once you get down to the base cases, you will have tried every single possibility for true and false for those variables, and you will have found every single way to make it true. You see that? So it's all coming together. Read those comments and all the instructions in the write-up, and those are the two major pieces of your lab. You're going to have the evaluation of a formula under a mapping, and now you know how to generate every possible mapping with recursion, trying possibilities. So this is definitely a lab that's going to force you to relearn recursion very quickly. Do yell at me if you have any questions about anything. So that's logic.cpp. The test is the testing program is here in testlogic.cpp. That's going to be what you're going to compile and make sure it all works. You'll use the make file, make testlogic, and just run it with /testlogic. And here are the tests. So I've made some helper functions that just like make a bunch of formulas easily, like make an and of two formulas very easily for me without having to like call make shared all over the place. So just come back up here. It should make enough sense. And here's a way to print out satisfying solutions, which I'll use to compare your results to mine. And here's some evaluation tests. So here's test eval. I make this exact formula, and here's how you do it. You make all the variables on the heap, because they're vars. Then you make a not, and you negate r, right? And then you and that with q, because that's q and not r. So here I am making a shared of and, q and not r. And then here's the whole formula, p ORed with q and not r. That's the original formula. See that? And so here's a variable to value mapping. P can be true, P can be false, Q can be true, R can be false. And then here is me evaluating that formula under that mapping. The answer should be true, right? So I'm making sure that's true. And then here's me evaluating the same formula under a different var-to-val mapping that makes it false, just making sure it's all working out, right? So that is evaluation tests, and then the rest are for your SATSolve function. Find all the satisfying solutions test. So here's a very simple formula. It's just P by itself. So only if P is true is the formula true. And here's a formula that is not P or Q.